Alright, so just before we get started, what I wanted to do is sort of walk through a high-level framework of what we're going to be doing today. Now, we're not going to be doing every single one of these steps, but typically when I'm building a machine learning model, these are some of the things that I will take in consideration. So first and foremost, we're going to be using our real estate data that we used the last time in one of our tutorials on predicting real estate prices based on a whole bunch of features, which we're going to walk through later today. So step number one is we need to go ahead and we need to prepare our data. And preparing our data includes things like removing unwanted columns. So we're going to go and look at specific columns that we are not going to be using. We're going to remove any empty fields if we have any. I don't believe we had any in this particular one. We're also going to fix any type of data structure, so data types. So if we have something that's a string and we want to convert it to an integer, we're going to look at stuff like that as well. So this is really about pre-processing your data, making sure that it's actually clean and ready to be used in some kind of a model. Now, one other thing I'll tell you is my team today of data scientists, a lot of their time is actually spent on building the data set. So making sure that the data set is actually clean and that it's usable. And that sometimes requires connecting different data sources, making sure that they make sense, cleaning them, cleansing the data. So there's a lot of time spent typically by data scientists just doing a lot of that. So understanding frameworks like pandas is actually very important. Then the next thing we're going to do is we're going to select the type of model that we want to use. So if I'm doing, like I said, a regression model, then I want to use that. I want to look at different types of regression algorithms. If I'm going to be using some kind of a classification model, then I want to look at classification models. And really, this is where you need to understand a bit of the mathematics. So when I am looking at a specific type of model, you need to have somewhat of a background, or at least educate yourself. Go on Google and educate yourself on exactly how a linear regression works, how a gradient boosting regression works, or a random forest regression works. And just having that understanding is going to help you understand and interpret those results as well, and better allow you to determine which models are best applicable for the different types of data sets that you're working with. Now, the next thing you're going to do is you're going to determine your independent and your dependent variables. And in that, you're going to understand what it is that you're trying to predict. So in our case, we're going to be predicting real estate housing prices, which is going to be our dependent variable. Then we have a whole bunch of independent variables, which are going to be your features. That can include things like the bedroom size, the lot size, if it's a waterfront location or not. So all of that stuff we're going to be looking at as well. Then you need to create your training set. So in this, you're going to be creating what we call a training set and a test set. And what that means is if I have an entire data set, you're going to allocate some of that or hold that back from actually fitting that into the model when you're training it, because you want to use that later on to test. And so say, for example, I've got 100 rows in my data or 1,000 rows in my data. If I'm holding back 20%, that means 20% of it is actually not going to be used in helping to train the model, because we're going to be using that to test later on. Now, scaling the data is something that you typically do want to do. We're not going to be doing that today because I'm going to be reserving that for a future tutorial. But essentially, you want to try scaling your data and normalizing it to make sure that when you are predicting it, you don't have one large variable that's swinging the overall value or the overall prediction, so to speak. So scaling the data could be anything, including making sure all your different features are between -1 and 1, so it'll just scale it up or down. Or between 0 and 1. So that's something that we typically would do, but we're going to forego that just for today. Then we're going to call something called the model.fit, or the .fit algorithm. And in that, we're going to pass in the training X variables and then the training Y variables. And so what we're going to ask the model to do is look at all the different training samples that are out there and compare it to the actual training Y. So if I do have 80% of my data set, I'm going to use all those features, and I'm going to tell the model that, listen, these are the features I want you to predict, and this is the actual value for Y. So create an algorithm so that it actually works out. And that's what we're going to be using in terms of testing our algorithm as well. And that's really what machine learning is about. That is, you're going to be consistently updating your features, updating the numbers, going back to the model and saying, here's now what the new Y is now that I found this new information out. And the model's always going to try to self-adjust itself based on new data that it gets, or new different features that it gets, or features that it needs to exclude. We're going to then test our model using a training test set. And then you're going to repeat that back and forth. And finally, once you're comfortable with the actual numbers with your test set, you're going to go ahead and predict some new values. So I just wanted to give you that background before we start getting into the model. So let's get into some of the modeling now. So in our previous tutorial, we talked a little bit about the data set regarding some of the real estate transactions when I did my video on Excel versus pandas. And if you haven't seen that, link is in the description. It's an awesome video, check it out. But as a part of that, we were also looking at some of the data sets in there, or the data set, sorry, in there. And we were seeing that there's probably some pre-processing we need to do. But one of the things I mentioned in the previous video is I actually wanted to figure out how we can go ahead and start predicting some of the real estate prices. So let me, just for a reminder, let's go back and re-import that data set here and take a quick look at it. So if you look at it, remember this data set had the date, it had the price that it sold for. So these are real estate transactions that happened in Washington State. So it has a whole bunch of characteristics on it. It has the price, bedrooms, bathrooms, different square feet configurations, whether you're looking at living, the entire lot, and so forth. And what we wanted to do is we wanted to say, can we actually take this data and predict any of the prices themselves? And if so, with what level of confidence can we do that? So today we're going to tinker in with what I would call the beginner level of machine learning modeling. So today we're going to go over a number of different models. We're going to go over the linear regression. We're going to go over decision tree regressor. I'm going to introduce something called a dummy regressor as well. One of my favorites is the random forest, whether it's a regressor or a classifier. I just like the way it works. And then the gradient boosting regressor as well. So we're going to look at 5 different algorithms. And in today's video, I'm going to be focusing on one specific metric. Typically speaking, when you're doing a regression model, you're going to be iterating through a couple of different metrics. You're looking at mean average error, mean square error, root mean square error, and then the R-square value. Today I'm going to be focusing specifically on root mean square error. And the reason why I'm doing that is because when you're looking at things like the R-square value, the R-square value is really good to tell you whether or not a model is more lenient towards having mostly been predicted through error or actually been predicted through the regression. But I like looking at root mean square error because you can actually compare across models and see what your error rate looks like. Now, I'm not saying this is the only metric that you should be looking at. You should be looking at all of them, but if I actually focus on all of the different metrics in this tutorial, we would literally be here for like hours, and I don't want to do that to you guys. So I'm going to focus on one of them, but in upcoming tutorials we'll look at different metrics and see how we look at things together. But root mean square error is a really good way to start. Okay, so first things first, what we need to do is we need to do a little bit of pre-processing with some of this data. So remember last time, one of the things I mentioned to you guys was that when I was looking at this data set, there are actually values in here that have zeros for price, which doesn't make a whole lot of sense. So if I just do a df describe on here, it'll show me that my min price for some of the sales were actually $0.00, which doesn't make a lot of sense at all. So that's one thing we need to take care of. The other thing, when I look at this data set, if you look at all the columns, you want to have a quick look through all of them to see whether or not they actually add a lot of value in terms of helping me predict different things with this prediction model. So if I look at, for example, something like country, it's USA across the entire board, so it doesn't really add a lot of value. So this is something that we're going to look at dropping. The other thing we're going to look at is street. So when we're looking at street, or when we're looking at any kind of data set whatsoever, you look at something called cardinality. And what that means is how many different unique combinations are within that one specific column. And if the cardinality is greater than some certain threshold that you set, then you may want to drop that column because it's not going to add a lot of value. So here, let me give you an example of what cardinality means. So if I look at a list here, and I'm just making this up here, and I look at A, B, C, D, E, and then I just add F, F, G, G, and so forth. Now, in a scenario like this, what cardinality is going to do is it's going to look through the list and it's going to look for all the different unique groupings. So A would be one group, B would be another, C, D, E, F is a group on its own, and G is a group on its own. And so the cardinality in this case would be 1, 2, 3, 4, 5, 6, 7. Now, if I added another G, my cardinality doesn't change because it still belongs to the G group. But the minute I add an L, that's a brand new group altogether, so my cardinality changes. Now, the reason why cardinality is really important is because when you're looking at variables that are not numbers, so they're text or string or whatever you want to call it, you have to do something called one-hot encoding, or label encoding and one-hot encoding. And what that means is you have to convert it to a number, because an algorithm is not going to be, or a machine learning algorithm like the ones we're going to look at today, are not going to be able to process text necessarily. So we need to figure out a way around that. And the problem is, if I have too many combinations, then I'm going to be adding numbers to something that, again, is not going to add a lot of value because they're going to be one-off. So if I look at street, I may have one or maybe 2 at most of these values in this entire column. So it doesn't make a whole lot of sense. Now, if you're in real estate, you're probably thinking to yourself, yeah, the street does make the sense because it's going to be dependent on, you know, whether it's an affluent street or an affluent area and all that other stuff. Well, all that's true, but then you can also use things like the zip code as a proxy, because your city and your street is going to be contained within a zip code. We do need some repeatability within the columns to actually make use of this, and there's not going to be much between street and city, really. If you think about it, you know, you can actually look at this at you know, at the city route, totally doable. But we're going to focus today on saying, how do we just look at it at the zip code level? And then if we find that our model's not strong enough, we can try to, you know, always drill down a little bit, or we can even try to drill up a little bit in some cases. So we're going to process this data in a way so that the state zip is actually just a number, because I want to get rid of the WA in there. I'm going to remove city and I'm going to remove street, and what that's going to leave us with is a model that's full of just numbers. In the future, I will be showing you how to do some modeling on text columns as well, and then in that case we're going to be using one-hot encoding. But for an introductory machine learning tutorial, I don't think that we should be getting into that today, but that will definitely come in due course as well. Alright, so let's take care of some of the first transformations that we talked about. Alright, so let's go ahead and get rid of the country. Let's try that. So to do that, we're going to say our data frame is going to be equal to the data frame dot drop. And what this means is we're just going to be dropping a certain number of columns, and we're going to say country. And then you have to define the axis. So your axis, if you have axis set is equal to 0, which is the default, I believe, then it's going to try to remove a column. Otherwise, if you set axis equal to 1, it's going to remove the row. So if I go ahead and hit enter and I reprint this data frame, so now when I look at this, you'll notice that my country is gone. I actually don't have it there. I can't scroll across anymore. So the other thing I want to take a look at now, if I go ahead and just run this, let me get rid of this, it's going to still show that I have a minimum price of 0. So to go ahead and address that, it's actually quite simple. So I say df is equal to df, and all I'm doing is I'm referencing this variable here within the data frame, and I'm just setting it greater than 0. So I'm saying now take a look at this specific variable price within this data frame, and now if there's anything greater than 0, only apply those and pull those. So when I pull this, you'll notice that, and if I try to do a describe on this, you'll notice that my minimum now is $7,800. So we've taken care of that issue as well. Alright, so the next thing I want to look at here is when I pull this, I want to see if I can get rid of the WA in front of state zip, and at the same time I think I'm going to try to rename state zip as well. So I've actually developed some of this code in advance just so you don't have to watch me type. I'm just going to copy and paste it and tell you what I'm doing here. So what this command is saying is df.rename. I'm looking at my column, which is state zip, and I'm replacing it with zip, and in place equals true just means that leave all the values there. And then I'm saying take my column df zip, which is going to be my new column, so then this is now going to be called zip, and replace anywhere where you have a WA with blank strings and treat that as an integer. So when I go ahead and run my df command on this, you'll see that it's now been renamed to zip, and this is actually gone as well. The W in front of it, that is. Now there's a few other things I want to take care of. Bathrooms 1.5, 2.5. I'm not sure, maybe this is an error with the data. But let's go ahead and take care of that for both bathrooms and floors. So all I want to do is I want to say treat this as an integer. So when I go ahead and copy and paste this code here, it's going to say df bathrooms is equal to, now treat df bathrooms as integer. So when I go ahead and run the data frame again, it's going to now round these or convert these back into the integer that they should have originally been, because you can't really have half a floor. You can technically have half a bathroom, so maybe we do leave that actually. So let me go back and change that. And you know what, let's just leave it, because sometimes you have half a bathroom or it doesn't have a tub or something. So maybe that's what they mean by it. But floors, let's go ahead and convert that. Alright, now in order for us to go ahead and, so let me get rid of this. In order for us to go ahead and set up our machine learning model, typically speaking, when you have any kind of a regression model, you're going to have a y variable and an x variable. So typically the most easiest type of regression is y is equal to mx plus b. And x is going to be your independent variable, y is your dependent variable, m is going to be your slope, b is going to be your intercept, and then you're also going to have some kind of an error as well. And so when we're going to be doing some kind of a regression model, we're going to be looking at what portion of the model is actually explained through the regression itself and what portion comes from the error. Now that's actually what the R-square value is really meant to do. We're not going to be going over that, but you can always go ahead and just do a quick R-square check on it. I'll put some resources in the description. If not, I will be covering that off in a future video as well. It's just I just don't want to get multiple concepts mixed up, especially for people that are new to this kind of modeling. So what we're going to say is y is going to actually be equal to, so let me bring up my data frame again. What we're trying to do is we're trying to predict price using all of these variables up here, and these variables are called features. So bedrooms, bathrooms, square feet, living, and all that stuff. These are individually called features. And what we're going to do is we're going to say, how do we use these features to predict the price? Okay, we're going to take care of these string values in just a second. You'll see how I'm going to do that. But for now, let's just go ahead and say I'm going to set my y variable equal to the price. So df price. Then I'm going to set my x variable, which is going to be all of this stuff over here, or my independent variables. And we're going to say df.drop price. And all that means is, in this scenario, I'm defining y as the price, and in this scenario, I'm dropping price out of this data frame and saying x is everything but price. So if I go ahead and print x here, and again, I forgot to define my axis, so axi equals 1. So when I go ahead and, you'll see that price has gone from this, but everything else is still part of the x-axis. And similarly, if I go ahead and print y, you'll see it's going to show all the different sales values. Alright, so now what I said to you is we're not going to be using any one-hot encoding in this one, so I can get rid of some of these strings. Now I can always go ahead and just drop this if I wanted to, but I'm going to show you something else. It's called a cardinality function, and what cardinality is, again, is they're different groupings. So what I'm trying to figure out here is I'm trying to say that when I look at my entire feature set here, because I'm going to be limiting this to my x variable, which remember has all of my features, how do I go through every single column to make sure that I don't have scenarios where I have groupings of text of greater than 10, in this case is what I've set up. You can set this to 100,000, whatever you want. But in my scenario, I'm just saying I want to make sure I don't have any groupings of text. Now, this is also going to look at something called objects. So when I go and do x.info up here, you're going to see that a lot of these are integers or floats. And typically speaking, this cardinality, we're going to limit it so that it's only going to be looking at objects, because we're excluding the number, any kind of a number basically out of here, which is done right there. And so it's going to look at daytime, it's going to look at any other object, and in this case, street and city are considered objects. Zip is not, because above we converted zip into an integer. So that's the reason why I converted zip, so that it doesn't get weeded out when we do this methodology here. So what is this saying? This is saying that I'm setting my maximum cardinality to 10 in this case. It's going to search for all the columns in all of these different features here. So it's going to go down every single one of these features, excluding all the numbers, and it's going to say if the number of unique variables is greater than 10, in this case, because that's what I set up, then drop that column. And so when we go ahead and look at this, and I print out X, it's actually dropped street, city, and date, because date was also considered a object as well, or as a datetime object. So in a scenario like this is where I like using something like this cardinality thing, because it makes it easy for me. Now, if there was some string characters that only had, say, 6 different unique items, or grouping, sorry, it would actually be here, and I would one-hot encode that. And one-hot encoding, again, just means that I'm converting it into a number array. So I'm not necessarily saying that, you know, married. So if I give you this example here, let's say I say married is equal to 2, I say divorced is equal to 1, and single is equal to 0. Now imagine I just had these strings in here. So I had married, divorced, single all across here somewhere. If I just converted that to 0, 1, and 2, that wouldn't make a whole lot of sense, because what I'm telling the algorithm is that 1 is greater than 0, and what I'm telling it is I'm saying divorced is greater than single, which doesn't make a whole lot of sense. Or married is greater than divorced, which is greater than single. What one hot encoding is going to do is it's going to add 3 more columns on top of this array here. So if, for example, my column was actually married, so let me go ahead and draw this actually, it's going to be easier. So if I were to draw this over here, and again I'm doing this with my mouse, so apologies if it's not that clean. And let's say I had a regular database here, and I had married, single, and I had divorced. What one hot encoding is going to do is it's going to take that, and we're going to go on to the other side here, is instead of it being an actual value, it's going to go up here as an additional column field. And what it's going to do is so whatever columns were here, let's say this is X, so this represents all of this stuff, that's still going to stay there, but it's pulled this column out, and it's basically made its own individual columns. And instead of it saying married, single, or divorced, it's actually going to say married is 100, divorced is 010, and then single is 001. And this way I don't actually go ahead, and because these are their own individual columns, I don't have any issue where I'm saying one is greater than the other. All this is saying is that married is present, divorced and single are not. Whereas in this one, I'm actually implying that 1 is greater than 2 and 2 is greater than 1 and 2 is greater than 0, which in context doesn't make a whole lot of sense. So that's kind of the reason why for today's exercise I avoided one hot encoding, because it is sort of complex, but we will go over that for sure. And you especially need to do one hot encoding when you're doing any kind of classification examples. So yes, no, cat, dog, rabbit, all those scenarios, because they are based on text for the most part, you will be doing a lot of one hot encoding in that as well, and we'll go over that, something like that in the future. Alright, so I've got my X variable set up here, which is cool. So the next thing I need to do now is I need to go ahead and create my training set. And so let me pull over my code here that I developed for training this data. So what this does is we're making use of a library in sklearn model selection, and we're using the train test split. What train test split does is it's going to take a certain portion of your data and it's going to hold it back for testing later on. So it's going to take a certain portion of your X, a certain portion of your Y training data, and then a certain portion of your X test and a certain part of your XY. So the way this works is, let's just say for X I had 100 rows. What it's going to do is I'm going to say my test size is 25% of that. So it's going to say of the 100 rows, 25 are going to go to X test and Y test, and 75 are going to be used to train the model at X train and Y train. And that's all this does. And this is just going to reshuffle around the order. So that's really all this is going to be doing here for us. So I've gone ahead and I've created our training set. Alright, so the next thing I want to do is I want to go ahead and bring in my models. So what does that mean? What that means is I want to go ahead and test a whole bunch of different models at once. And I want to see whether or not at the same time one is better than the other when it comes to root mean square error. And so if you're wondering what root mean square error is when we're looking at the X test, that is considered your actual value, because we're taking a piece of history and we're putting it aside to test for later. Then you're going to have your Y predicted. And in this case, your Y predicted is going to be whatever your model is going to be predicting. And let's say the value here is 10, and the value for Y predicted is 12. What it's going to be doing, and it's going to do this, a whole bunch of times down this, it'll be 7 and then 15 or whatever it is it's going to take the difference of these two, it's going to square it, and then it's going to take the square root of that, and it'll add that. It basically takes a sum of all of that as it goes down. And so what that does is it's a really good way of measuring whether or not, or how close your predicted value is to your actual test value. So if you were to think of a regression line going like this, and this is your y-axis and your x-axis, typically in linear regression, if this is your regression line, you want to see if this is one value, this is another value, this is another value. It's going to be measuring this distance here. And it's going to say how far apart am I from every single time that I am predicting my value versus testing my value. And when you do the root mean squared error, it eliminates a little bit of error, we'll call it. And it gives for a little bit of better judgment on how well your model is working, because it's going to look at how far from an absolute value you are from where you should be in terms of your predicted value. When we run the graphs, you'll see what I'm talking about. So what I've done is I run something called the dummy regressor. What a dummy regressor does is it's going to be looking at just the average of whatever that data set is going to, whatever the trained data set we're throwing at it. It's just going to say, okay, what is the average of the overall prices for this? So it's really just saying my best strategy is I'm just looking at the average and that's it. And so what we want to do is we want to benchmark against the dummy regressor to see how well some of these other models are going to be predicting. So I've gone ahead and added in a few of these myself. I didn't, sometimes I play around with it, sometimes leave it at the default. If you want to know again what these means, click here somewhere and just hit Shift Tab, and then you can go down, hit the plus sign, and again, it'll tell you about all of these different things, what they do, and you can read about it down here as well. So it's a good resource. So what I'm saying is, in this case, I'm defining a list called models, and in this I have a whole bunch of different models that we're going to be testing out. So I've got dummy regressor, random forest regressor, decision tree regressor, gradient boosting regressor, and the linear regression model as well. And then I've just defined a random data frame here that's going to be holding some of our results based on what gets passed into this temp. So you'll see how this works in a sec. So let's go ahead and bring in the next bit of code. And so we're going to go ahead and run this. Hopefully no errors. Good. Alright, so this next bit of code, what this is going to do is it's going to iterate through every single one of these models that I've got up here. So it's going to say for model and model. So the first one's going to be the dummy regressor. It's going to print what it's called. And then we're going to say, okay, we're going to fit that based on the X train and Y train data that we have. Again, I'm optimizing for root mean square error for the price. So the way you calculate that is you import something called the mean square error from sklearn. And so what that is, that's going to be, like y minus y predicted squared. And then because I want to take the square root of that, I just also imported a function from the math library called square root. And so to get that value, you just take the square root of your mean square error, which is going to be y test. And then this is y predicted, because this is just me saying, well, what is it going to predict if I throw in the x test against this first model, which is going to be the dummy regressor. So this is the same thing as y predict, by the way. I could easily define it up here if I wanted to. It's just easier to do it this way. Then we're going to print the root mean square error. And then we're going to append those results to this data frame that we set up. Alright, so now when I go ahead and run this, what it's going to do is it's going to iterate through all of these different models, and it's going to tell me what I'm looking for is the random mean square error. So what this is saying is that every single time I predict, this is $375,000 off of where it should be. Or sorry, $375,000 off of the actual predicted value if I just use the dummy regressor. Alright, if I use random forest, it's saying I'm $249-ish thousand off. When I use the the decision tree regressor, it's about $500,000 off. And when I use the gradient boosting, it's about $270,000 off, and linear regression does the best at this. And so I need to go ahead and rerun some of this stuff because my graph didn't come out how I wanted it to come. So the problem is I ran it too many times, and so it just threw a bunch of errors. So I just got to go back and reinitialize some of these variables. So this just shows you in a graphical format. If you look at this, it's saying that my linear regression and my random forest regressors are probably performing the best with the gradient boosting algorithm fairly close by. And this is a good way. So the lower the number, the better in this case, because I want to try to minimize the error. So the quicker we can get this to 0, which is going to be impossible, at least from experience, but the goal is to get this as close as possible to 0. And if you can get that, then that means that most of your model, when you compare one next to the other, is actually predicting very close to the predicted line. Now, I will tell you, I went and I played around with some of these configurations. They're not fully optimized at all. So when I defined these models up here, I did play around with some of these different arguments in here. So for example, I changed the learning rate from 0.01 to 0.1. The max depth for some of these decision trees, I changed those as well. So I played around. I mean, there are certain cases where I can change this to 100 and you'll see that the number is going to go up, which is not good. Or I can change it to 5 and the number is going to go up, which is not good. So you really need to find that sweet spot. And I don't think I found that sweet spot. I was just tinkering with it a little bit. And then you can look at the number of estimators. So the problem is, in a tutorial like this, it's hard for me to go and actually show you and help you understand all the different algorithms and what they mean and how they work, because that's a session on their own. So my suggestion to you would be to go ahead and look at some of these different regression models and do a little bit of research on how it works mathematically speaking. But as we go through these tutorials, we will be talking a little bit more about those as well, for sure. Now you may be thinking, if we go back and just quickly run a df.describe, one of the things you may be thinking is, wait a minute, my average price is about $557,000, and you mean to tell me that most of the times I'm off, in some cases even more, which I'll explain why so in a second. How's that any good? I mean, that's a pretty high error threshold. Now, what if I actually told you this is not too bad? It needs a little bit more tweaking. And so one of the things I will tell you also about machine learning, keep in mind, is people are consistently upgrading their models and their algorithms. This is when they mean that machine learning needs to be a learning model. We haven't talked about a few things. One of them being, we haven't even done any kind of feature engineering right now. What we've done is we've assumed up here that all of these different features that we had looked at are actually applicable to these regression models. But when you do something called feature engineering, it'll actually sift through all these different features and it'll say, well, this one's important, this one is, and so forth. And then it'll also tell you the ones that are not that important. So to get a tighter fit to the actual line, you can start, getting rid of some of these different features that aren't that important, and then go ahead and rerun your models and see whether or not you get a better fit or not. So feature engineering is something we're going to cover off for sure in an upcoming tutorial. Now the other thing, for some of you who may have already figured this out, this is a real estate data set. And what do they always say about real estate? Location, location, location. What we've done is we've assumed that the landscape is the same across every single zip code in Washington. When in fact we know that, in certain areas, you're going to have certain places that are more affluent, certain places that are less affluent, certain places that are higher to average price increases per year, and other places that are not. So to really get a better understanding of whether or not this is going to be a good model for us to use, is we need to go ahead and do something called bin the data, which we're not going to do today. That's going to be reserved for an upcoming tutorial. But what that basically means is I need to now say, all right, in Washington state, maybe there's 5 zip codes that are clustered together in one specific area where the average income is, $100,000. But there's another 5 that are sitting somewhere else where the average income is $30,000, and that's also reflected in the real estate price as well. So you need to categorize your different zips into something called a bin, and you can define the number of bins, whether it's 1, 3, 5, 7, it doesn't matter, whatever makes sense. We can play around with that later on. But when you start binning the data, you'll actually see that the model is actually even, in most cases, a better, tighter fit. Now, I'm not overly familiar with Washington State. I'm from Canada. More specifically, I understand the Ontario real estate market very well, which is a province here in Canada. Now, it'd be unfair for me to say that Thunder Bay, for example, and Mississauga, Ontario, or Toronto, Ontario, have a similar real estate landscape, and we know that's not the case. So I can't treat them with the same brush. In which case, I would need to go ahead and say, how do I take these different zip codes that are in here and separate them out, and then add some other kind of functionality or some other kind of data into this. So we need to introduce some new data as well. And that data is going to have to be something like the average income in that zip code, or something that's going to help me understand how do I categorize this. And so that's going to be reserved for an upcoming tutorial. Today we looked at a whole bunch of different linear regression models. We looked at a data set. We took a look at how do we do a little bit of filtering out of that. So a little bit of common sense to say, let's get rid of the country code. Some cleanup to say, making sure that the price is actually greater than 0. We did a little bit of renaming with some of the columns as well. And we got rid of some specific text in there as well. So if you noticed, I specifically picked these so that I can show you different functions that you can do in order to help pre-process some of your data. What we haven't gone through yet is if you have missing data, or if you have data that's swaying more to one way than the other. So for example, if I look at a specific data set and 80% of it are yeses and 20% are no's, it's not going to typically always predict the best in that case as well. So there's other things you'd look at as well. We also looked at how to convert specific data frame objects into integers. And then what we looked at is we said, how do we start taking a look at our y variable and our x variable? Let me get rid of this here. I showed you how to use this cardinality function, or this cardinality little algorithm here, which I encourage you guys to use. It's a great way for you to, keep a little bit of control in terms of how much you want to focus on when it comes to one-hot encoding and how big you want your data set to be, because your data set can easily go from 20 columns, and I kid you not, to 50, to 150, 200 columns if you don't do a little bit of cardinality in there as well. We looked at a very popular scikit tool called train test split and how to train and test your data. Then we looked at building out some actual models, and we looked at different scores. And finally, we looked at one of the characteristics that you would look at, or one of the metrics you would look at, and that's a root mean squared error. And again, I'm not saying this is all you focus on. There's definitely other things you focus on as well. But this is a big one that I would look at, especially when I'm doing some kind of a forecasting model. All right, so in one of the upcoming tutorials, we are going to go ahead and add some more data. I'm going to be getting some data on zip codes, specifically around income, average income in that area. So maybe we'll use that. How I'm getting it, I'm going to be using some good old-fashioned data science practices to procure that data. But ultimately, we're going to look at that data and see, can we actually apply it to this and get a better score or not? So we'll take a look at that. But this was a very quick introduction to data modeling. I encourage you to take a look at this. I'm going to put this code up on GitHub. So take a look at this, go through it, try to understand it. Always go on Stack Overflow. It's a great source as well. If you have questions, post them in the comments. I'll do my best to help as well. But that in a nutshell is an introduction to machine learning using regression modeling. All right, guys, if you like that introduction to machine learning modeling, please don't forget to like, comment, share, and subscribe. It really helps out. And again, appreciate your support and look for more upcoming tutorials in this space. Thanks very much.